These are our notes for Wednesday 8th. Go full screen here. I did pass out a new note packet, and that is linked on the slide if you need to copy that off from home if you were absent. So we're going to go in kind of three pieces here. What we did in class today is we took some notes, and then they got in groups and worked on the homework, and then their homework is to watch notes on 5.3, which are Edpuzzled on today's slide. So the first thing we talk about is what we call the extreme value theorem. We abbreviated the EVT. There's not a whole lot to it. A couple things to note, that in the hypothesis, the function has to be continuous over a closed interval. So let's talk about what that means. It means we have to have closed dots at the beginning and the end to be guaranteed anything by this theorem. We also can't lift our pencil as we travel. Notice it doesn't say that the function has to be differentiable. So we can go up, we can go down, and if we feel like it, we can even make a cusp, and maybe we just want to kind of mosey around. But that function right there is continuous on the closed interval from A to B. You are guaranteed at least one absolutely lowest point. In this case, its existence is right here. And at least one absolutely highest point. In this case, it's up here. Okay? So that's our EVT. It doesn't really require much practice. It's very common sense. So today, in addition to the EVT, which I just told you, we're going to talk about the difference between what we call global, sometimes called absolute, extreme values. Those are maxes and or mins. These actually mean the same thing. It kind of depends on your curriculum, your teacher, your professor. I use absolute, but now if you see the word global maximum, it means the absolute highest the function ever gets. You are not guaranteed the existence of one, though, unless the function is continuous on a closed interval. This guy right here has no absolute max. You might say, yeah, it's right before I get to that open dot. But if that open dot was at 4, I don't know if that's that 3.9999999 till I croak over and die and somebody continues. I can't grab it. So we can't have extrema at open circles or undefined points. We also have what's called a relative extrema. I like that word relative better than local because it kind of means in relation to the stuff around it. Technically, it's on an open interval if it's the highest or lowest there. Like in pre-calculus, you would do relative extrema on sort of a nice function like this. You'd say, well, that is a relative max. It is the highest point on that open interval. This is a relative min because it is the lowest point on an open interval. Relative max, relative min. This guy actually is also the absolute max, which is what I would call it. You're like, don't I call it both? It is both, but like I said in class today, if I said somebody was holding a square and they said, hey, look at this rectangle I've got. And I said, well, you've got a square? And they say, yeah, but every square is also a rectangle. I'd use the more strong definition. So the stronger to call that an absolute max versus a relative, although technically it's both. Okay? So another thing to watch out for, doesn't necessarily happen on the AP test, but it does deserve some thought, is how about right here? Is this point not the highest point on that open interval? And we'd say yes. So this guy right here, its strongest definition is that it's the absolute max. But it actually is also a relative max. Right here, this closed point is the lowest point on this open interval. So that is technically, by definition, a relative min. Relative to the defined points next to it, it is the lowest. Right here, this is a relative min because in relation to the points to the left and directly to the right, it is the lowest. So just kind of be careful about that. We'll go practice it right here. It says find all extreme values. All right, so as I travel around this function, I notice that this is the absolute lowest y value of any defined point on that graph. So I would say that there's an absolute min. It's always the y value because it's the extrema of f, and f is y equals. So it's an absolute min of 1 at x equals -3. All right, then I travel around and getting higher and higher and higher, and then we start to turn. So we had a max there. It's the absolute max, though. It's also a relative. But we're going to write absolute max of 5 at x equals 0. This guy right here, though, I've got to be a little careful with that because on this open interval right here, if you look at the points to the left and to the right, it is the lowest. It's not the absolute lowest of the function because these y values are lower, but it is a relative min at of, I could say at of or of at, but I like to say of to at x equals 1. Now the next thing, stuff to beware, never ever list an undefined point as either one. So open circles are not candidates for any kind of defined extrema. Endpoints, though, that's up for debate. It kind of depends on mathematicians debate about it, professors debate about it, books say it differently. You'll find there might be some mathematicians very well educated across the world who say that cannot be a relative min, and I'd say, but it is smaller than all the defined points directly next to it. But someone else might argue, yeah, but there's none over on the other side of which to compare it to. I personally am fine with either, so I don't write either because it's more to write. But if somebody told me that right here at this defined point, it is a relative min because relative to the defined points next to it, it is the smallest, I'd accept it. But I don't require you to write it, and I won't mark it wrong if you don't. So you get to pick. Most people pick not writing it because it's less to write. So let's go take this. I would pause and do this one on your own. That's what we did in class. But remember, this doesn't count as anything. I travel, and I hit not only a relative max, but an absolute max of 3. It's the highest y value that function has ever defined. At x equals -1 is where it's defined. And then I'm getting lower and lower and lower and lower. I do not hit any kind of a minimum because we're not defined there. But right here where I am defined, I am the highest y value on that open interval. So I actually have a rel max of 1 at 1. This guy over here, although defined, is not the absolute minimum because all of these defined points are less than it. We can't call this one it because this function does not have an absolute minimum. You might say, LaRue, that violates the EVT. I want you to go back up and look at the EVT carefully. It says if a function is continuous on the closed interval, then you're guaranteed. We're only not continuous. We're also not on closed interval. So I'm not guaranteed that I have them. I could. Maybe it goes up like that, right? And goes like that. Okay, let's do that. This function is not continuous. It's not on a closed interval, but I do happen to have an absolute max and an absolute min. I'm just not guaranteed their existence. All right, so let's talk about the calculus that happens here at our extreme values. So you'll notice right here, absolute max, also a relative max. Why it's not writing for me. All right, so right there, right here, rel min, rel max, rel min. Somebody this morning said that's an absolute min. I said no, because of these. We're not on a closed interval, and those are going forever. And a rel max. Let's talk about the calculus that occurs here. In particular, the slopes of the tangent lines. 0, so the derivative is 0. 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 And right here, right? Those derivatives aren't approaching each other from the left and from the right, so the derivative doesn't exist. These x values, where those things happen, those possible extreme values, are called critical values. The points at which they exist are called critical points, and that's our next task of the day, is to figure out how do we find critical points of a function. First thing we do is we take a derivative using all of our derivative techniques that we've learned so far. In number 3 here, to find the derivative, I just use my power rule. I get x squared minus 9. Okay, I don't have a graph, but I also noticed that my derivative was always either 0 or non-existent at those extreme values. So we decide what makes the derivative, let's just say f prime, or what makes f prime of x non-existent. Okay, for this one, we basically just set the derivative equal to 0, and if it's not a fraction, this one, it'll just factor nicely. And this one has 2 critical values, and I'm done. If I have a fraction, then I set the numerator equal to 0. So this has a critical value at x equals -5 if this was my derivative. Okay? I also have a place where the derivative does not exist, but I have to be careful whether I call that a critical value or not. Okay? We're going to have 2 warnings up here when I'm done. Okay? Warning number 1. Watch out for vertical asymptotes. Remember, those make the denominator equal to 0. They're x values for which the denominator is equal to 0 and the numerator is not. So in this case, I have a vertical asymptote at x equals 2 and also x equals plus or minus 2. That's a place of interest. Things can happen definitely to the left and the right of an asymptote, but I can't have a critical value there. I can't have a point on it at which the function turns. Okay, so we have to watch out for our vertical asymptotes when we do this one, but let's go take the derivative. That's actually 4 minus x squared to the -1/2. So we're going to use our chain rule, -1/2, 4 minus x squared to the -3/2 times the derivative of the guts, which is -2x. We always clean that up, making that a positive x. Getting rid of these. And then we always get rid of our negative exponents. This is a square root of 4 minus x squared quantitatively cubed, right? So when I look at where the derivative equals 0, I only need to focus on the numerator. A fraction can't be 0 unless the numerator is. So I do have a critical value at x equals 0. To determine where the derivative doesn't exist, I look at what makes the denominator 0. And in this case, it's a plus or minus 2. But they can't be called critical values because they're not in the domain of the function. They're actually vertical asymptotes. So this one would just have 1 critical value at x equals 0. Its critical point would be at what I get. Let's change this to values so I don't have to plug that stuff back in. So my other thing I'm going to tell you to watch out for, it doesn't happen very often, but don't leave the domain of the function. Okay? If you get a derivative equaling 0 or non-existent, maybe your derivative was, I don't know. Maybe you had like a square root of x squared minus 9 and you got a 2. You just left the domain of the function because that has you square rooting negatives. So you just kind of got to watch out for domains you've got to watch out for vertical asymptotes. So the next thing we did in class is they were in groups, and they did 1 through 8 together in a group. The key is posted. You should go do those now. And then we stopped, and we did 8 and 10 together. So I'm not going to stop my video. You should have. And we're going to go do this one. We have h prime of x being 2 cosine of x halves times the derivative of the guts. The 2's cancel. So my derivative of this function is cosine x over 2. I need that derivative to equal 0 on the domain given or non-existent. But the cosine function's all roly-poly, so I know there's no value that I can't put in for x. Its domain is all reals. The domain of my function, though, is negative 2 pi to pi. So I have to find out where we're equal to 0. And I'm going to kind of head to the positive here. I have a cosine of 0 when the angle, I'm going to call it theta, is pi over 2. So that means x over 2 has to equal pi over 2. So x equals pi is one critical value as long as it is in the domain, which it is. Then as I travel around here, I get 3 pi over 2. Okay, so I need my angle argument to be 3 pi over 2. So I need x over 2 to equal 3 pi over 2, which means x would equal 3 pi. But my domain ended at 2 pi, so that's out. So from 0 to 2 pi, I found one viable critical value. As I go negative, right, I'm going to have that same issue, except over here be at negative pi over 2. So my cosine, just a second, right here, be at negative pi over 2 does work in that domain. I'd have x over 2 equaling negative pi over 2, so x would equal negative pi, which again is in the domain. So this had 2 critical values. The last one, the most important one, is this number 10. I'm going to hop onto my computer here while whoever was absent pulls out a calculator. And for this guy, what we do is we're calculator active. And so I think I should have my calculator from last hour still sitting up here. Hopefully I still have it entered. So I'm going to go to my y equals and enter it. Make sure you close that x right there before you hit the squaring. And again, you can pause. Our function was sine x squared over x. Sine of x quantitatively squared. Somebody asked if I needed parentheses around the sine. As long as you close it right here, your calculator's been programmed to interpret that as squaring the sine, not the x. Okay? So then I go to my window and I set it to the domain of my problem, which was 0 to 10. Okay, I can go by ones. I think this defaulted when I first did it. I zoomed in and stuff, so it changed my window. But I think it was like that. And we went and hit graph. All right, so you have to keep in mind what this is the graph of. This is the graph of y equaling f prime of x. Critical values occur where the derivative, which is f prime, which is y, equals 0 or doesn't exist. I definitely see one right here. So there's definitely one. In class, we weren't sure about this over here. Now on mine you can see it's crossing in the domain, but on the calculator screen it was smaller, so they couldn't quite tell. So I told them to zoom in or trace, like go over here and just I think if I enter a 1, it'll just head over there anyway. So if I go trace over there, I'm watching my y values to see if they do go negative, and you see they do. Okay, so between 0 and 1, that is 1 right there. There's 1 right here. We were really unsure about this one over here, so on trace I think I'm going to send it over to 5. We weren't quite sure what the deal was here. It's so dang close we couldn't tell. You have multiple options, all right? What you can do, don't just guess, because it actually turns out this isn't a 0. Some people said they wanted to zoom in on that to see if they could see a gap. And after they zoomed in 2 or 3 times, they could, and so they knew to discard this as a 0. Somebody else said they tried to Calc 0 there, or Calc Max, or Calc 0, either one. So if I go second Calc, if I try to do a Calc 0 there, interestingly enough, when I get to the left, whoops, sorry, let's get clearly to the left of that possible x-intercept, and let's go clearly to the bottom of it, hit enter, and my calculator says there's no sign change, which means it was negative and was negative the whole time. It never changed to positive. If it had changed to positive, you have to pass through 0. That's the EVT in the programming of your calculator. Kind of cool, right? So back to my graph. I want to head back to that graph if it'll let me. Let me go second quit. Another way to decide, again, is to do Calc Max. So you could also go second Calc, and you could choose the maximum on an open interval that includes the point in question. So I could go over here and I could hit enter, and I could go over here and hit enter, and if that's not a 0 for my y value, which it isn't, it's a negative 0.00, so close, but it doesn't touch. So the answer to number 10 is 2, and then we skip number 11. So the homework was, in class we finished 1 through 10 in groups, and then the homework is to watch the 5.4 notes, which are linked right here, and they're Edpuzzled. So come in with the 5.4 notes watched tomorrow. Have a good one, guys.